So the first basic technique for root finding are, are known as bracketed methods. So bracketed methods assume that we know an interval over which the function changes sign. Thus we require a lower bound xl and an upper bound xu. Because the function changes sign in that interval, and that's a precursor to being able to use bracketing methods, there must be at least one root in between. It is possible, however, that there might be more than one root. And if there is more than one root, we're not too sure which one we would find. That's a separate problem, however, to the basic idea. So the basic algorithm for bracketing methods is, first of all, we make a guess for the root based on the bounds. I'm not going to describe how we make that guess yet. I'm just trying to explain the basic underlying algorithm. So somehow we choose a new guess, xr, that's based on xl and xu. And I've written that here as it's some function of these two bounds. And we'll come to that later. Okay, so we've found some new guess for the root. We'll call it xr. It lies somewhere in between xl and xu. The next thing we need to do is to see how big the function value is at xr. If the absolute value of the function value there is less than epsilon, where epsilon is the tolerance that we're prepared to accept as an error, then we say we have found the root. However, if the function value there is bigger than epsilon, or if the absolute value of the function is bigger than epsilon, then we're not prepared to accept that level of error. And what we need to then do is somehow choose a new interval. By choosing a new interval, what that means here is not replacing both bounds, but it's replacing either x lower or x upper with the current value for the root. So somehow we've got to get rid of one of the old values of xl and xu, replace it with xr. We then go through and we repeat steps in 1 and 2 until our new guess for the root, finally the function value there, is less than our tolerance. Okay, so how do we choose the new interval? We do this by looking at the function values at the points that we've got. So we've got 3 points, xl, x upper, the bounds, and xr. We only have to choose one of the bounds for this algorithm, and we can choose x lower or we can choose x upper. In these slides here, I'm going to choose x lower. It doesn't make really any difference which one we do. We'll get the same result. So we look at the function value at x lower. That's that green point on the left here, and the function value at the root, xr, and we say if we multiply those two together, if they have the same sign, then the product of the function values there is going to be greater than 0. If the product is greater than 0, it means that the root cannot lie between x lower and x root. It's got to lie in the upper interval. So the root must lie between xr and xu. And so we set the new x lower to be equal to the x value of the root. And then we go through and we do the process again. If, however, the function value at x lower and the function value at our guess for the root f of xr are less than 0, in other words, the function changes sign between xl and xr, then that means the root must lie between xl and xr. Therefore, we set the new upper bound to be equal to the current value of the root, xr. So that's the basic process for choosing our new interval. The only thing left to do now is to determine the next guess. We have two basic choices in how to do this. The first is known as the bisection method, where we choose our new guess as simply the midpoint of xl and x upper. And so that's that point there. And as a functional form, we just say that xr is equal to 1/2 of xl plus xu. And this here is this function of xl and x upper that I was talking about before. Okay, that's the bisection method. It's the simplest approach. The other one is the method of false position. And so at the lower bound and the upper bound, we can calculate the function values, f of xl, f of xu. We then draw the straight line between those points, and where that chord crosses the x-axis, we say that's our new guess for the root. So we draw a straight line between the points. The functional form of this expression is equal to that. I don't expect you to remember that, but I do expect you to be able to derive this. Okay, so this is the function of XL and X upper that I talked about previously. It's based on the idea of similar triangles. So if we look at this triangle formed here, and we look at this little triangle at the top here, they are similar triangles, and so we can base our value of XR on this information. And I'm going to leave that as an exercise for you to do. So now we have everything we need to use bracketing methods.